Hey all, welcome back. This is Dr. Gardner at the University of Montana, and today we're going to be doing a introduction to partial differential equations. Just a real general overview on what is a partial differential equation, how do we read it, and then some real basics on what it means to solve a partial differential equation. This is really light stuff and not heavy. You can, of course, get an entire PhD in partial differential equations and how you solve them. Here, we're just a real brief introduction. So get out your pens and papers and we'll start our lecture. If you're a buff at PDEs, then you might want to skip this lecture and go on. But we will put this discussion of PDEs a little more in context of groundwater modeling and groundwater flow. So let's recall the groundwater flow equation. Here I will share my notes screen here, and away we go. So recall the groundwater flow equation, which we derived in previous lectures. And we'll start off with a general equation for saturated, fully saturated, confined aquifer flow. Okay, and this was our groundwater flow equation. Again, this is for fully confined flow in a fully saturated flow, often in a confined aquifer here. And more compactly, just another version you might see them in. dH dt is equal to grad. Oh, sorry, mistake. K bar grad H, where this upside down triangle is the gradient operator. Okay, so this is a partial differential equation. We derived it based upon conservation of mass, and it is a describes the behavior of head, in particular the change in head as a function of the change in head in time as a function of the change in head in space. All right, and some key indicators that you've got a partial differential equation. Well, one is these squiggle D's. All right, that's the partial differential operator. All right, so this guy means you've got a partial differential equation, and you can read this partial. One thing that helps me is to break this out into language, and so you can read the partial differential operator. So let's say we have this one, d dx here. We would read this as the change in whatever this operator is occurring to. So the change in something with respect to WRT, with respect to X. All right, so for example, this top term says the change with respect to X of the hydraulic conductivity times the change with respect to of head with respect to X. All right, so this operator right here says the change in head with respect to X. That is, it is very simplest point of view. It's the slope of the head in the X direction right at a particular point. All right, and the key of a partial differential equation is that it incorporates these differentials in different dimensions. So here we have dimensions of x, y, z, and t. All right, and so we're going to take a derivative of the head field with respect to the x direction alone. That's basically the slope in the x direction. The differential of the head field with respect to the y direction, that's essentially the slope in the y direction. And the differential of the head with respect to z, that's the difference in the z direction, right? Same with time here, t. And, to give you an intuitive sense of what this means is, if we're standing on a mountain, like the mountain outside of campus here, the slope of that mountain depends upon the direction I go. So if I'm standing on the mountain and I take a step south on Mount Sentinel, I'll contour on the mountain and I won't lose any elevation at all. If I take a step to the west, I'll go downhill. All right, I'll have a steep negative slope. If I take a step to the north, I'll contour again. And if I take a step to the east, I'll go up the hill. All right, so different slopes depending upon which way I walk on the hill. And that's essentially what these partial differential or partial derivatives are saying. So there's some key parts to a partial differential equation. And I'm going to use PDE from now on when I mean partial differential equation. So here are some parts. So t, x, y, z, these are my independent variables. Independent variables, all right? The location in space does not depend upon my x location, does not depend upon my y location. It does not depend upon my z location. It doesn't depend upon time. And it doesn't depend upon head. It's independent. All right, so these things are my independent variables. All right. H here is my dependent variable. This is the groundwater head, and it very much depends upon where I am in space and time. All right, so H is my dependent variable. Okay, so we have independent variables, dependent variables, and now a really important feature are these guys here. Use orange. These are my parameters. So here we have K and SS, and these are called parameters. And they are values that control the response of H, or what are they? Yeah, values that control the response of the head field. All right, so they're important in controlling, for instance, how the head changes with time. SS controls how head changes with time. K helps control how, the spatial variance of the head field changes. So these guys are parameters. Right, and so here I have two parameters, K and SS. All right, I have one dependent variable, that's H, my head, the field of groundwater head, and I have four independent variables, T, X, Y, and Z. All right. So those are the parts. So some other things we can think about. Well, the number of independent variables is really the dimensionality. So we'll oftentimes refer to a three-dimensional partial differential equation, for example. Well, this is really the number of independent variables. So here I have t, x, y, and z. So really this is a four-dimensional partial differential equation. However, in the field, we tend to refer to dimensionality as the spatial dimensions. So here I have x, y, and z. So this would be a three-dimensional problem. And then we refer to whether or not it's changing with respect to time with some other terms. All right. So in our nomenclature for in modeling nomenclature, at least for groundwater and for other fields, dimensionality refers to spatial variables. So x, y, z in our example. All right. And then the change in time all right. If we're considering a field where the groundwater head changes in time, so if dH dt is not equal to 0, we call this transient. All right, so in our case here, dH dt is not equal to 0 in general. I mean, it could be, but because we've specified a value here, it's not in general equal to 0. It means the head changes with time, and we call that a transient simulation. If dH dt is equal to 0, so for example, if I wrote this left-hand side here as 0, I state that the change in head with time is equal to 0, then I imply a steady state. All right, so just in the nomenclature, we tend to break up the time derivative and the x, y, and z derivatives. And so if there is time variance, if dH dt is allowed to change, then we're in a transient. If dH dt is specified to be 0, so the head is steady all the time, then we're in steady state. Okay. Some other things here. So for an example, before we move on, our particular equation here is a three-dimensional x, y, and z transient partial differential equation, 3D transient partial differential equation, or is considering three-dimensional transient groundwater flow. So parameters, let's zoom in on these guys a little bit. Parameters are these values that control system behavior. They don't change the shape or talk about this later, but they're not going to necessarily change the type of solution or the function that gives us a solution, but they're going to change how that function behaves. All right, and there's two types of parameters. So parameters can be independent of my dependent, not my, of the dependent variable. All right. So for example, here, K is not a function of the head. All right. K is independent of the head. And up here, you know, here K has, we haven't written it that K has any dependence upon the value of the head. It is independent of the value of the head. All right. So for example, K does not depend on head. And in this case, my PDE is linear. All right. So in this case, I have a linear partial differential equation because neither my storage nor my hydraulic conductivity is written as a function of head. All right. The linearity of a partial differential equation actually has nothing to do with, say, the shape of the solution. The shape of the head field will be, you know, some function that has curves and is not a straight line, but has everything to do with whether these parameters depend upon the dependent variable. All right. So if dependent on dependent variable, so for example, if my hydraulic conductivity is a function of the hydraulic head, all right, that means the parameter that controls my response depends upon the value of the head at that point. All right, we get this really coupled feedback in our system, and these are called nonlinear PDEs. All right, so that's not the case the way we've written our equation here. It's not the case for this one, but nonlinear PDEs are something that we encounter a lot. In fact, if we want to solve the equation for unsaturated or partially saturated groundwater flow, then our hydraulic conductivity depends upon the head. All right, and we have a nonlinear equation. But here for the fully saturated case, K is not dependent upon head, it's independent of head, and we have a linear partial differential equation. Okay, another thing that we can do when we look at, so we can, you know, so when we look at the PDE, we've already learned we can analyze different things. We can look at what dimensions. So are we looking at 3-dimensional flow or 2-dimensional flow? Are we saying that the head is constant with time, steady state, or are we saying that the head varies with time, transient? All right. But we can also look at how the parameters change with respect to the independent variables. All right, so for example, in our equation right now, we say d dx k dh dx. All right. This k is within a spatial term. That means here that the value of k can change with respect to x. All right. So right now, k can change as a function of x. All right, written this way, k is some value and it can change as a function of x. And in hydrogeology, this is a special definition. This is called heterogeneous conductivity. All right, that means the conductivity can change spatially. Now, if I have constant, so let's say I assume k constant in space, all right, so it doesn't change with, that means k doesn't change with respect to x, all right? Well, what can I do with a constant in a derivative? I can pull it out of the derivative, right? Calculus 1, so k bar d squared h dx squared, that is the second derivative of head with respect to x, all right? This implies homogeneous k in the x direction. All right, if it doesn't change as a function of x, then I can pull it out of the derivative and I can simplify my equation. So the location of the parameter in here tells me, oh, I'm considering heterogeneity, or nope, I'm considering homogeneity. All right. Okay, so the shape or the form of the PDE can tell me a lot. So for example, if I have this equation, all right, and I bring the k out here. Well, this implies that I'm homogeneous, all right, because the k is not in my derivatives, my spatial derivatives. 0 implies that I'm not, my head is not changing with time, so it's steady state. And I can simplify this one further. Oh, and I only have two dimensions, x and y, so I'm only considering flow in the x and the y direction, all right? So I'm two-dimensional, steady state, homogeneous. And if I can simplify this one easier, I just pulled this k out to sort of illustrate. Well, if I divide both sides by k, I'm going to end up with 0. So I get to Laplace's equation. Well, two-dimensional Laplace's equation. All right. And this is valid for steady state, homogeneous, 2D flow. All right. So if I see this, if I see this partial differential equation, I know exactly what the people using it were thinking about doing. They were thinking about a homogeneous two-dimensional flow system, which for various reasons, we may want to assume that our groundwater system behaves that way because there's lots of good equations and solutions to Laplace's equation. So let's move on now and talk about what a solution to a PDE is. All right. So let's add another page. All right. So again, analysis and solving of partial differential equations is a very rigorous field, and here we're just dipping our toes. But let's just talk a bit generally about what a solution is. So a solution to a PDE and there's a reason why I put A. There can be more than one. All right, so a solution to a PDE is a function that gives the value of the dependent variable. All right, so in our case, H, for all values of independent variables. All right, so this function would give us H for any X, Y, Z, or T. I see I've written X twice here. So for any value of Z or X or Y or T, this function will give us the value of H. All right, and it will honor all will honor the initial condition, which is the starting point. So if we have a head field that changes with time, this function will produce our starting head field at time equals to 0. All right, and it will honor all the boundary condition all the boundary conditions. All right, and so what boundary conditions are, let's say we're interested in, for example, we want to know what the groundwater head looks like in an aquifer. This aquifer has boundaries that control what's happening inside the aquifer. So for example, we might be receiving recharge across the top of the aquifer. We might have a river or a lake on the side that sets the head conditions. These are boundary conditions that control or are forcing conditions. So boundary conditions are forcing conditions that control our aquifer response. All right. So what we get when we seek some function that is some function of space and time that will give us the head at any point in space, at any point in time, and honors our initial conditions and our boundary conditions. All right. And so solving a PDE is also called solving the boundary value problem. All right, and if you're a mathematician who studies PDEs and how do we derive solutions, this is probably a more commonly used term, solving the boundary value problem. How do we derive a function that honors our boundary conditions and gives us the value of our dependent variable within our domain of interest, so inside our boundaries for all values of the independent variables. All right, so there's some ingredients for solving the BVP. All right, and anytime you want to solve a boundary value problem or a partial differential equation, you need these ingredients. All right, so the first is a domain of interest. All right, and in a domain of interest, like, in our case, it might be an aquifer. All right, a particular aquifer. So, in advanced hydrogeology, we're class at University of Montana, we're interested in, for example, the alluvial aquifer near Lolo, Montana. All right, that's our domain of interest. We need our governing equation. Okay, what PDE encompasses the correct physical processes adequate for us to simulate our system in order to solve our problem. So, for example, the groundwater flow equation that we discussed at the beginning of this lecture. All right, if we need to simulate three-dimensional, fully saturated, transient groundwater flow, well, then this groundwater flow equation will work for us. All right, the important thing is that the governing equation encompasses the physics we need to properly simulate our setting and answer the question that we are after. And the other thing is we're always trying to make our governing equation as simple as possible, because the more complex and more physics that we add into it, the more parameters and knobs we have that we don't know about. All right, so then the other thing we need are parameter values. So in groundwater and in groundwater modeling, and the governing equations we can usually come up with, we know the physics pretty well, and we usually know our domain of interest pretty well, but we really start to get into problems with the parameters. So K here, in our problem, K and SS, the hydraulic conductivity and storativity, how those vary in space and in time are unknown. All right, and big unknowns, but we need those. We need boundary conditions. And again, another source of uncertainty in groundwater. Boundary conditions are unknown, but things that are boundary conditions might be things like the recharge rate to the aquifer. Surface water conditions that set head at the boundaries. All right. All these things we may or may not know very well. For example, the recharge rate, pretty unknown. We don't know very well, but a very important boundary condition. And then the final thing we need is the initial conditions. So this only makes sense if we're considering a system where the head changes in time, for example. So we have a transient system. Well, then if we have a transient system, we need to know where to start. So this is the starting conditions. And this is really uncertain for groundwater modeling, because, for example, if we're trying to simulate an aquifer, when do you start the time equals to 0? Is it when that aquifer was first deposited and then fully saturated, or is it some head field that you interpolate and decide as the starting condition? Unknown. So initial conditions can be tricky, but they only make sense if we have a transient condition. So for groundwater modeling, if our DHDT doesn't equal to 0, right, that means we've got a transient condition and we need to know what our starting condition is. Okay, so the entire art and science of groundwater modeling is the assembly of these ingredients. All right, so it's the assembly of 1 through 5. And the correct degree of uncertainty in 1 through 5. And then finally, making sure that our ingredients solve the question we're interested in solving. So, for example, in many cases, we may not need to consider 3-dimensional flow. So figuring out what partial differential equation we even want to solve is important. How do we get our hydraulic conductivity mapped? All of these are the art and science of modeling, and what a lot of what we're going to do is think about how do we put these pieces together, and then use these pieces to solve groundwater flow problems. So groundwater modeling, at its very heart, right, is not learning a software suite. It is learning how to put together the 5 ingredients to solve the boundary value problem. And we're going to start looking at some ways that we solve PDEs without groundwater modeling first. And so, for example, we will get into solving partial differential equations with our first step, which is an analytical solution. All right, and an analytical solution is an actual function that we can write, i.e. head is equal to a function of x, y, z, and t, that will satisfy our PDE, our BCs, and our initial condition. All right. We can only find these analytical solutions for as we'll see, just finding one for a very simple problem, it can be quite hard and arduous. Solving them for very complex situations is, you know, a worthwhile endeavor and far beyond the scope of this class. But you know, we'll get our introduction to analytical solutions next. All right, thank you for joining us, and we'll talk to you later.